Hello, this is Mushtaba Akbari from University of Alberta. I am a PhD student working in the telerobotic and biorobotic system group under the supervision of Dr. Mehdi Tawakkoli. I'm glad of having the opportunity to present our paper here. I appreciate your time in advance. Ultrasound is a widely used modality in medical imaging. It is a safe and low-cost medical image modality, but it has low signal-to-noise ratio compared to other modalities like CT or MRI. The orientation of the probe and sufficient contact between tissue and the probe are key factors for capturing high-quality ultrasound image. Breast cancer is the most commonly diagnosed cancer among women aged 30 to 39. Commonly treatment options for breast cancers are mastectomy, where the breast is removed, and lumpectomy, where the tumor and a portion of adjacent tissue are removed. Lumpectomy, followed by radiation therapy, and the area previously occupied by tumor is filled with a body fluid called seroma. The seroma needs to be segmented for accurate needle insertion during radiation therapy. This motivates us to propose a US scanning algorithm for breast that guarantees the visibility of the stroma inside ultrasound frame. There are three important features that we have considered for proposing our US scanning algorithm. The first one is the visibility of the stroma inside each frame, as it is essential for this application. The second one is the real-time feature that is very important as it should work in control loop, and the third one is the adaptation of the algorithm to compensate the variation of the breast shape while scanning. In this paper, we propose a visual servoing algorithm that controls 5 DoFs of the robot during the scanning of the breast. The proposed method has two phases, called pre-scan and post-scan, to analyze the geometrical features of the stroma and design a controller to keep the stroma in the field of view. In pre-scan phase, we manually segment the stroma in the frames and extract geometrical features of the stroma, while in post-scan, we move and orient the probe using visual servoing algorithm. The setup is shown in this figure. We use Panda robotic arm for moving the probe on the surface of the breast, and the image is being sent to the host computer in real time with the frame grabber. In this paper, we have three main contributions compared with the state-of-the-art methods. Our method's first contribution is using ultrasound in both pre-scan and post-scan phases. That is advantageous over previous methods that use other modalities like MRI in the pre-scan phase. The second novelty of our proposed method is proposing a new set of features in designing trajectory and controlling the orientation of the probe in visual servoing stage to guarantee the visibility of the seroma inside the ultrasound frame and sufficient contact between tissue and the probe during the scanning. The result of this algorithm is a series of high-quality ultrasound images that can be used for further research steps like 3D reconstructions. During scanning trajectory planning, the proposed system extracts necessary information from breast and stroma in the pre-scan phase, including the location of the stroma inside the tissue. Then US image visual servoing algorithm controls the US probe's orientation and position in the post-scan phase utilizing the location of the seroma from the pre-scan. The pre-scan phase. The probe will be moved on the surface of the breast, either manually by sonographer or some naive autonomous US scan. The position and orientation of the probe at each point is being recorded for further processing. The contour of the stroma and region of interest will then be manually segmented to estimate the location and shape of the stroma. The stroma inside the breast will be approximated as an ellipsoid for geometrical analysis simplification. Multiple frames are being assigned to the surface of the breast and probe to track the movement of the probe during post-scan and relate this movement to each other for estimating location and shape of the stroma as shown in the figure. E is the ellipsoid frame, U is the US frame for each pixel's value, and B is the base frame. Transformation from US probe frame to the base frame is important for our controller and shown in the equation. The geometrical information of the ellipsoid calculated in the pre-scan phase is being used for calculating desired value of in-plane and out-of-plane rotation and XYZ position of the probe. We define orientation in axial plane as in-plane rotation, and the orientation out of this plane as out-of-plane rotation. The in-plane rotation and the movement of the probe in the z direction of base frame is being updated in post-scan phase. We calculate desired XYZ trajectory of the probe on the surface of the breast based on the intersection of a plane containing the principal axis of the ellipsoid and orient it with the orientation of this axis to have maximum alignment with surface normal of the breast surface. This trajectory will then be a curve on the surface of the breast. These trajectory points create a set of points, and a sample trajectory and surface normal of the breast containing stroma is shown in this figure. We use intersecting plane frame C for calculating desired out-of-plane rotation. The out-of-plane rotation is designed to sweep the US probe smoothly on the trajectory that is always pointed toward the target point PO in frame C. This point is a point that the line passing through the center of the ellipsoid from the surface of the breast intersects with two separate tangents originated from beginning and end point of the trajectory. The equation for calculating out-of-plane rotation is as follows, and the figure shows the procedure for a sample breast containing stroma. The process for calculating in-plane rotation in sagittal view of the breast is shown in this figure. Here we are using center of ellipsoid PM in frame B, which was found from pre-scan images. We consider surface normal of the breast so that the probe is kept in a natural orientation with respect to the surface of the breast. This is shown in equation that finds the angle which maximizes the dot product between normal vector and the candidate vector. The surface normal is found using the second equation, which considers the point on the surface of the breast follows 3D equation. Using visual servoing techniques, we now refine the in-plane rotation of the probe and downward pressure applied to the tissue according to information from the US image confidence map and the segmentation of the stroma in the US frame. The US confidence map is commonly used per processing method. It is a per pixel measure calculating the probability of a random walk starting from each pixel to reach a number of virtual transducer elements under specific US constraints. This method considers image as a graph where nodes represent the pixels and edges interconnecting the nodes. We implemented 4 connected neighborhoods for each pixel nodes in confidence map. The mean value of confidence map C-mean can be used for controlling the contact between tissue and the probe. We compare this value with the desired value of C-mean in the controller for adjusting downward position. In this equation, S is the area of the confidence map and M and N are the dimension of S. The center of mass of the segmented object is a measure that indicates whether the image intensities are well divided over the segmented region or not. This feature is useful for controlling in-plane rotation of the probe in visual servoing algorithm. The location of center of mass is found using this equation and is shown in the figure, where background intensities have 0 values and foreground intensities are 1. Our segmentation algorithm uses outsourced threshold method to create a binary image and select largest connected component as the stroma inside the breast. The angle between the central image and the line passing through the center of mass, as determined from the center of scan line, defines an error that can be used to control the in-plane rotation of the probe. This is shown mathematically in the equation and graphically in the figure. The right figure shows the output of the segmentation algorithm, and the error corresponds to the location of the center of mass. We can now describe a control law for the position and orientation of the US probe in probe frame D. The error is the seek-stuff difference between the current and the desired trajectory in each point of the trajectory. The error is an input to the PID controller to control both position and orientation of the probe during scanning. The image acquisition block, which is a US machine, sends an image to the host computer for calculating confidence maps mean and center of mass position error. Then a PID controller adjusts the position and orientation of the probe. The control loop is shown in this figure. The algorithm is demonstrated here. where epsilon and delta 1 and delta 2 are the tolerance of the position and orientation error in the proposed system. This algorithm shows the visual servoing procedure that controls the position and orientation of the probe in each point of the trajectory to reach the tolerance value of the error. In this study, an Axia 80 M20 force-torque sensor is mounted on a Panda robotic arm, and an adapter was built to hold US probe. The US machine used for this experiment was an ultrasonics touch with a linear Foley transducer. For this experiment, we only used the 2D functionality of the US probe. Images from US machine were captured in real time with an EpiFan for processing. For our experiment, we used a tissue phantom made of plastisol. The controller was programmed and implemented in MATLAB. The communication between robot and computer was done over UDP. In the pre-scan phase, we moved the probe on the surface of the tissue and recorded the force applied to the tissue and US probe position. We designed our post-scan trajectory based on the output of pre-scan phase. The experiment results for 5 different points on the trajectory have been reported in this figure. The error is the norm 2 of difference between the current and desired value for each point, which converge to 0 as time passes. The force values also remains in the reasonable interval during an experiment as reported in the last figure. The value of beta converged to 0, which proves that our method keeps the stroma in the center of the image as time passes. The average value of each metric is reported in the table for each point during the experiment. In conclusion, we defined 5 DoF US scanning methods based on the geometrical analysis of the stroma in 2 phases. In pre-scan phase, images were processed to extract geometrical information of the stroma inside the breast. In post-scan, we calculated desired trajectory to move and orient the probe on the surface of the breast. The visual servoing algorithm updates 2DoF in real time. The proposed method was evaluated using plastisol tissue. We are planning to work on a 3D reconstruction algorithm that is able to generate a 3D volume of the breast using high-quality ultrasound images. We are also planning to work on finding new sets of features that can be added to the system to control the probe when a needle is inserted inside the breast. This research was supported by the Canada Foundation for Innovation (CFI), the Natural Science and Engineering Research Council (NSERC) of Canada, the Canadian Institute of Health Research (CIHI), and the Alberta Jobs, Economy and Innovations Ministry's major initiative funds. Thank you very much.